When I was young, I had this odd fascination with old steam engines. So every chance I got, I would pester my parents to take me to the railway museum where I could see these huge old engines in their full glory. One of the things I was always curious about in these engines was the presence of this huge heavy wheel like the one that you see here. And this was called a flywheel. And it always confused me why this thing exists on the engine, because it is huge and heavy and it is not connected to the track. So what is the purpose of putting something so heavy on the engine unless it has some kind of benefit? But you will see this structure called a flywheel in many places. You will see it in generators, you will see it in household instruments, you will see it in all kinds of dynamos and other applications. And in all of these cases, it is executing the same function. And we are going to understand why it is used in this way. In physics, there is the concept of analogues, or a set of quantities which have similar relations to each other as another set of quantities. Let's review a few. So here we have two different sets of quantities which have similar relationships. For example, we have angular acceleration denoted by alpha and its counterpart linear acceleration denoted by small a. We have angular momentum that is denoted by capital L, and we have linear momentum that is denoted by P. And we have torque denoted by tau, that is also called moment, and we have its other equivalent, that is the force exerted on an object. Now we have this really basic concept in mechanics called inertia, which is the tendency of an object to maintain its state and resist any change in its current state. So a question arises, what is the rotational analog for inertia? If acceleration has its analog in rotation as angular acceleration, if we have angular momentum for linear momentum, if we have torque corresponding to force, then what is the rotational equivalent of inertia? Let's find out. So in order to understand this, first we have to revise a few concepts. So here we have two identical objects, one of which is rotating and the other is not. The rotating object can be considered to be a set of particles, all of which are working in a sense together. But the speeds of these particles will not be uniform because of the rotation. If you see, points farther away from the rotating center will be moving at a faster linear speed compared to points closer to the axis of rotation. So if we take any point I, the velocity of that point, the linear velocity or tangential velocity of that point will be equal to omega multiplied by Ri. Ri is the distance of that point from the axis of rotation, and omega is the angular speed or angular velocity of the rotation. Now, the kinetic energy of any given particle is given by the familiar old formula K is equal to half mv square. But here, in the case of rotation, we are not considering the movement of a single particle. We are considering the collective sum of the movement of several particles. So we will have to apply summation to this. So we have the total kinetic energy given by capital K is equal to the sum of the individual kinetic energies of all the particles in that rotating system. If we substitute the formula for linear velocity in terms of angular velocity, that is Vi is equal to omega Ri, we can change the equation for kinetic energy in terms of rotation. So here we have Ki, that is the kinetic energy of the ith particle, is equal to half times m times Ri omega. So in this particular case, if we substitute the value of Vi as omega Ri in Ki is equal to half mvi square, half mvi square is the value of the linear kinetic energy of each particle moving through space. Putting this new value here, we get a new formula, that is Ki is equal to half mi times omega square times Ri squared. So finally, we can interchange these terms and we can bring m and Ri square to one side and omega square separately. Now we know that the total kinetic energy of the rotating system is equal to the sum of all the individual kinetic energies, as we can see in this equation. So we can add up all the individual particles' kinetic energies using this equation. Here we understand that omega is common to all the particles and it is same for all the particles. It doesn't matter if the particle is close to the axis of rotation or far away, the angular speed for all the particles will be the same. So we can take omega as common to all these particles and take it out, and we can leave the rest inside. So if we compare this with the formula for kinetic energy, V square and omega square are analogues of each other. In the same way, the term here that you see, summation 1 to n of mi times ri square, is the analog for mass in the case of linear kinetic energy. In other words, mass and this term here are the analogues of each other. So we have learned the concept that mass is essentially inertia. So here what we have is the rotational analog of inertia. So if you see here, this particular term performs the same function for kinetic energy as the mass of an object does for kinetic energy moving in a straight line. So half k times I omega square is the formula for rotational kinetic energy, while k is equal to half mv square is the formula for translational kinetic energy. You will see that we have replaced this term with a single letter I, which has the same role here as m is playing in the other equation. And this term I is what we call moment of inertia. So the moment of inertia is given as summation of I 1 to n, that is all the particles in the system, the mass of each particle multiplied by Ri squared. Now, here is the critical difference between moment of inertia and inertia. The inertia of an object is a single unchanging quantity. But as we can see here, moment of inertia depends on the distance of the particular particle from the axis of rotation. This tells us that I is not a fixed quantity because an object can be of many different shapes but have the same mass. So an object can have different moments of inertia provided that the mass remains the same but the shape of the object is changed. We will see a few examples shortly. So here we have a thin circular ring. And as you can see, this ring can be rotated along two separate axes, and these two different axes will have different moments of inertia. So in the first case, the moment of inertia is simply I is equal to mr square. In this case, the axis of rotation is perpendicular to the plane of the disk. In the second case, the axis of rotation is passing through the plane of the disk. So you can think of the disk as rotating edgewise, and in this case, the moment of inertia is equal to mr square divided by 2. For a solid circular disk, again, we can have two different orientations. But in this case, we have I is equal to mr square for one orientation, and for the other, it is I is equal to mr square by 4. For a hollow cylinder, the moment of inertia is equal to mr square, while for a solid cylinder, the moment of inertia is mr square by 2. You will notice that the moment of inertia for a hollow cylinder is actually higher than a solid cylinder, provided the masses are same. This is because in the case of a hollow cylinder, most of the mass is located farther away from the rotation axis as compared to the solid cylinder. For a solid sphere, as long as the rotation axis passes through the center of the sphere, the moment of inertia is equal to 2 mr square divided by 5. This is regardless of the orientation of the spin axis. For a thin rod, the moment of inertia is ml square divided by 12. So what are the physical dimensions of the moment of inertia? From the formula we see that it is m, that is mass, multiplied by r square. So that is the dimension L squared. So the dimension for moment of inertia is equal to m times L to the power 2. The SI unit for moment of inertia is kilograms meter square. So coming back to the question of what is the purpose of this flywheel? We understood that for objects moving in a straight line, the heavier the object, the more its inertia, which means that it will resist any change in its movement better. In the case of a rotating object, the greater its moment of inertia, the lesser the changes in its rate of rotation. It will not speed up quickly, it will also not slow down quickly. In this case, you will notice that the flywheel is built in such a way that most of the mass is as far away from the rotation axis as possible. This maximizes the moment of inertia. But why is this useful to us? In the case of any engine or generator or many toys, we want a constant rate of rotation. We don't want the object spinning too fast or spinning too slow or changing its spin very quickly. To minimize the change in the rate of spin, to minimize the change in the rate of rotation, we are using these structures called flywheels, which enable the object to rotate at a much more uniform and even rate. So, is it possible to find the moment of inertia of an axis that is parallel to another known or given axis? Let's find out. Let's summarize what we have done so far.
Manorama Horizon. Learning made simple.